Morning, eighth graders. Today we are going to talk about how seismologists figure out where the epicenter of an earthquake is. Remember that the epicenter is the area on land directly above the break in the rock that happens underground. And seismologists need to figure out exactly where that is, not because so they can assess damage. I mean, the damage is pretty obvious after an earthquake happens, but they want to know exactly where that break is underground because that area underground is now compromised. It's now weak, and another earthquake could happen in that same area. And so they kind of want to flag these areas on Earth that have these ruptures underground, okay? It says here on this site, and you guys are going to be going to this site to practice a couple of these. I'm going to walk through one with you. It says that earthquakes occur because of a sudden release of stored energy. Okay, so our tectonic plates are always moving and they're pushing together and they're moving past each other, and those rocks will catch and build up a lot of energy. And it can only build up for so long before it actually gives. Just like when I showed you the bending meter stick, right? It can bend to a certain point before all that kinetic or that potential energy turns into kinetic energy and it snaps. The sudden motion causes shock waves, okay? So waves just like any other waves that'll radiate from the point of origin called the focus and travel through the earth. Okay, so again, if we had a kiddie pool of water and I tapped the center of that water, waves would go out in all direction. Same thing happens underneath the ground. Okay, a rock breaks underground and it sends waves out in all directions. And it goes all the way through the earth. So even if there is an earthquake that happens in California, those waves actually do reach our seismic stations here in Minnesota. The waves are so weak by the time they get to us, but we can still track them on seismographs, okay? Each year there are thousands of earthquakes that can be felt by people, and over 1 million that are strong enough to be recorded by instruments. Okay, so 1 million of them are recorded by instruments. We don't feel them all, but we can actually track those movements underground. Strong seismic waves can cause great local damage and they can travel large distances, but even weaker seismic waves can travel far and can be detected by sensitive scientific instruments called seismographs. And sometimes dogs, like this one, can trigger seismic waves, and seismic stations will pick up those movements by the dog. Say hi, Nietzsche. A seismic wave is simply a means of transferring energy from one spot to another within the earth. Okay, so there's a lot of different kinds of seismic waves. The two that we are going to be focusing on are called P waves, stands for primary, and S waves, secondary waves. These are the two types of waves that seismologists need to pay attention to in order to figure out where the epicenter is. Okay? P waves and S waves move at different rates. They move at different speeds. So they all start from the focus, they all start from the break in the rock, and they radiate out in all directions, but P waves actually travel faster. Okay, so like if my forehead is the surface of the earth and the break in the rock happens underground at my nose, these two waves are going to travel, they're going to leave at the same time, but the P wave is going to arrive first and then the S wave. And the further it has to travel, the deeper the earthquake is underground, the longer the period of time that lapses between the arrival of the P wave and the arrival of the S wave. Okay, and that is the part that we're really focused in on. We are trying to figure out how much time lapses between the arrival of the P wave and the S wave. All right, so when an earthquake happens, a seismic station will start recording as soon as that P wave arrives, and then it will track how many minutes go by or fractions of a minute go by until the S wave catches up. All right, so what that looks like on a seismograph, which is the document that a seismogram puts out. Seismograph is the machine. Seismogram is the actual document. Sorry, I get that mixed up. There's always this quaking, okay? So you'll never have a nice flat line. The Earth is always moving, okay? And then you'll see this big jump, and that is when the P wave comes in, okay? And some time goes by, and then the next big jump on a seismogram is the arrival of the S wave. And we can figure out, based on the distance between these two big jumps, we can figure out how many minutes that is. And that plays a really, really big part in figuring out where the epicenter is. All right? So we are going to give this a shot. We're going to walk through San Francisco area, and then I'm going to have you guys try Southern California, the Japan region, and Mexico on your own. Actually, if you come to the Zoom class, we'll do Southern California together, and then you guys are going to do Japan and Mexico on your own and answer the question on the Google Classroom. All right, so San Francisco area, I have that submitted. Here is a map of the region that we're going to be looking at. All right, so say you're hanging out here in San Francisco and the ground shakes. Okay. The first thing you are going to do is look at the seismogram from that area and figure out the distance between these two. Okay, so let's do that. Okay, so here are 3 seismograms, and we always need 3, and that'll become apparent in just a second. Okay, so let's say we're in San Francisco, there's an earthquake, and so we call up another seismic station, and these are located all over the world. We have them here in Minnesota, they have them all over in California, and because you're in San Francisco and there's so much shaking going on, you decide to call your buddy in Eureka, California, and say, hey, look at the seismogram that just came in and tell me how many seconds went by or lapsed in between this P wave right here and this S wave. Okay, so looking at this, we can see that the P wave comes in at time 0, right? Because it doesn't start until that P wave comes. And then if we look here, we've got 40 seconds here. We have 50 seconds here, and it kind of looks like it's coming right at the 50-second mark, okay? So we're going to type in 50 right here. Okay, and that's great. Thank you, people in Eureka. But we need more information, and so we have to make a couple more calls. So we call our friends in Elko, Nevada, and you can see that this seismogram isn't as intense, right? And that we can infer then that this is further away from the epicenter. There's not as much shaking. Remember, waves will lose their energy the further they go. All right, so here's a P wave coming in at time 0, and then it fizzles out a little bit, and then right here it starts to kind of jack back up. And we've got 70 seconds here, 80 here. Each of these lines is worth, let's see, 2, 4, 6, 8. Yeah, each of these lines is worth 2. So it looks like that S wave is coming in at 72 seconds. So 72 seconds lapsed between the arrival of the P wave and the S wave. Okay, and we're going to call, the last call we're going to make is Las Vegas, Nevada. Do the same thing. First P wave came in at time 0, and then we look at when the S wave came in, and that would be at 62, 64 seconds. Type that in here. All right. And we'll go to convert. Okay, so then seismologists have this really cool graph that can take that time interval and it can convert it into how many kilometers each of those locations are from the actual earthquake epicenter. Kind of cool. All right, so if we look here, we said in Eureka, California, there was 50 seconds that came, that happened in between the P and the S wave. All right, so if we go up here and we look at the line that says 50 and where this line crosses it, it is right, see where it crosses it right there? We go down here. This is in kilometers. Okay, so we've got 400, 420, 440, 460, 480, 500, and this line crosses it right at 480 kilometers, okay? So type that in there. Elko, Nevada. Elko, Nevada was at 72 seconds. Okay, so that's way up here. Here's 70, 72. And that line crosses the 72 mark. It's hard to see. It's right before the 700 kilometers. So we'll say 690 kilometers. 690. And then Las Vegas was at 64. Oh wait, I apologize. Each of these lines is worth 1, it looks like. So 71 and 2. It's a little higher. Yeah, 72 came right in at 700 kilometers. And then this last one, 64 seconds, 61, 2, 3, 4 seconds. That line crossed right at 620 kilometers. Okay, whoopsie. And then we're going to find the epicenter. Okay, just by using this graph and using that interval time, find the epicenter here. Okay, and it says, excellent work, we did it correctly. Okay, so what we're looking at right here is in Eureka, California. That was the first place we called. They looked at the interval. They plugged it into that graph to figure out how many kilometers the epicenter was from that location, but they had no idea in which direction, right? They just knew that it was X amount of kilometers away. And so they would take a compass, and they've obviously got computerized versions of this now, but if we were in class together, we would take a compass and we would do the radius of that distance, and we would make a circle all the way around Eureka. Okay, so that's what you see here. The point of the compass is here, and they made a circle around here. In Las Vegas, they did the same thing. They had their distance, they set their distance, and they made a circle all the way around Las Vegas. And then the last one was in Elko, Nevada. They put the point here, they figured out the distance, and they made a circle all the way around Elko, Nevada. Well, what you'll notice here, and the reason why we need 3 seismic stations, is that all of these circles intersect only at one spot, okay? And that spot is just south of San Francisco right here. And that would be where the epicenter is. So we would know then, seismologists would know that underground here in San Francisco, right at this exact location, that is where the break in the rock happened, okay? The next part of this is we can compute the magnitude, meaning how strong was the earthquake. All right, and we use what's called the amplitude of the waves to figure that out. The amplitude is the distance between this 0 millimeter line and how far up or how far down the shaking goes. Okay, it's kind of like a heartbeat monitor, you know? The amplitude will always swing up as much as it swings down. So we're only looking at one of these sections here. I'm gonna go to the next page. And we use a whole different scale. Seismologists have made all of these cool little graphs for us to use. All right. So here in Eureka, this was the seismogram that they had. And here's the 0 mark. If we go to the highest amplitude mark up here, let's see, each line is worth 10. Okay, so here's 250, 260, 270, 285, maybe? The lines are kind of making my eyeballs bug out. All right, and Elko, Nevada, we can see that it was much weaker, right? And that makes sense because we know that that epicenter is south of San Francisco. Elko, Nevada is quite a distance away. So it was 700 kilometers. We see that the highest line here goes to 50. 60, wait, no, 50, 50, 60, 70, 80, 90, yeah, okay. So we'll say it's 60. And then down here in Vegas, we can see that the highest line hits right at 100. Oops. I'm gonna look back up here and make sure I did this one right. 250, 60, 70, yeah, okay. And now we're gonna submit this, and they will all cross. Okay, so here's the distance, and then the amplitude, and they just cross the lines here, and they all meet again at one spot. And so the amplitude, or the magnitude, sorry, of this earthquake is going to be a 7.2, 7.1. See how that goes, 7.1, which is a pretty strong earthquake. Confirm. And it says, congratulations, you have done a great job. Yay for me. All right. So what I would like for you to do is on our Zoom call, we will have gone through, if we go back to the beginning of this little simulation, we're going to do Southern California together. And then I would like for you to do the Japan region and the Mexico region. And then in the Google Classroom, you are going to describe to me geographically where that epicenter is. Okay, so for instance, in this one, I would have said just south of San Francisco. Okay, so wherever it is on your map of Japan, you can use the directions of the towns that they have listed and say what direction from, you know, a landmark is the epicenter. Another thing I'd like for you to do is I've posted this P&S earthquake waves video that Mr. McCormick and I are demonstrating. Okay, so this shows a little kind of a demonstration of how both waves move from the original break in the rock outward to the epicenter. Okay, so watch this video that you're watching now, watch the P&S earthquake waves, and then I will post that website for you to try to triangulate 2 other earthquake waves. All right, give it a shot and see how you do.